Okay, so we're moving on to 2.2, and we're really going to talk more about the limit idea. So if you didn't get limits down in pre-cal, then we're going to review that some, okay? So let's talk about something. How does the function f of x equals x squared minus 1 divided by x minus 1 behave? What's happening with this guy near x equals 1? Can this thing exist at x equals 1? No. Because why? There's a hole there. So if you put this guy in your calculator, what would you get? If you go in there, try it. Put this thing in your calculator, in your y equals, let's see. Top needs to be in parentheses, so x squared minus 1 divided by parentheses. Do what? It's a TI emulator software that we purchased. And so when I could use it on my dock camera, but sometimes it's easier to just pull it up here and do it. And the nice thing about here is when I hit graph, I can take that guy and drag him over here, and he comes into my notes. So that's kind of cool if I wanted to have him there. I don't know that I do, but anyway. So what do we see there? A straight line? Do we see the hole that's really there? We don't see it on the graphing calculator, but there is a hole there. It's been removed. You can remove it. How can you remove it? Can you factor that thing? I gotta get rid of that little graph thing because it messed up. If we factor this, x squared minus 1 factors to these two, right? Do you remember that? And so now those go away, and so I've got y equals x plus 1. That was what this picture was, y equals x plus 1. It's what's called a removable discontinuity. It's discontinued at that little hole. Our graphing calculator can't show us that. But I'll show you a picture right here. There's the hole at 1. When you factor it, you get this, and that hole is removed. Same line, actually, but there's really a hole because our original function cannot exist at x equals 1. There is a hole there, and you would have to note that. Now, you can remove it by factoring it, but you know, that's the deal. And if you in your calculator did the table and you said if x is 1, what do you get? If we go here and we go to second table and I put in 1, no, 1. I think my table's set up wrong. Hold on. Yep. What do I get? Error. Even though on the graph on the calculator it looks like it's fine, it's not fine because there's a hole there. And so the behavior, as we get close to 1, as x get close to 1, what does y get close to? What number is the y value that we're close to? 2. Now, if you plug in x equals 1, you don't get 2. But the limit, as x gets close to 1, that's where we are, okay? And if you look over here at your table, this is a table of values. Those are all close to 1, right? And what are these all close to? 2. We get ultimately close to 2. We can't ever actually get there. That's that whole idea of a limit. All right, but remember I said you could plug in and you could get a value? Well, this isn't polynomial. That's why we can't just plug in. But if we factor and we get down here as x approaches 1 of this, I factor it and I end up with that business, right? And gone and gone. So now as x approaches 1, I can plug in. What's 1 plus 1? 2. So the limit of this is 2. Limit It does not have to be defined at that point, which is what we have. We have a limit that's not defined in the function. That's okay. Okay? Is that ringing a bell from pre-cal? Anybody besides you? Or you guys that had calculus already, is that ringing a bell? The limit can exist where the function is not defined. Okay? And then here we've got some limit laws. You don't need to write those down. They're here. They'll be in your notes. The sum of two functions as x approaches c, you can just combine the two limits. There's some different things. What I really want to get to is some techniques for doing limits algebraically. And this is that algebra that you just want to kick yourself sometimes. But, all right, if we were doing this limit, you always want to look at it and say, could I plug in? Could I just get the limit? Well, if I plug in 1, what happens to the bottom of that? Goes to 0. So we can't direct substitute. So try factoring. That's the first thing you want to try. So if I factor the top, I've got x plus 2 and x minus 1. On the bottom, I've got x times x minus 1, which allows me to cancel out. And now I'm taking the limit as x approaches 1 of this. Does that work? Yeah, substitute 1, and you get 1 plus 2 over 1, which is 3. Okay? So, if it doesn't do direct substitution, try factoring, see if that works. It's not going to always work. Does that make sense? To try and fix it by factoring. All right, but this one, what about this guy? Square root of x squared plus 100 minus 10 over x squared. Can we let x go to 0? We can't plug in x to be 0 on the bottom, right? And I don't think factoring that thing's going to help us. So here's another technique. When you see radicals, sometimes you want to multiply by the conjugate of the radical expression. What is a conjugate? The opposite sign. So it would be square root of x squared plus 100 plus 10. And we can do that because we're going to multiply on top and bottom. So here I go. This is the conjugate. So if I do that over itself, that's just like multiplying by 1, and I'm allowed to do that. When you multiply by conjugates, the reason you do that, what happens? You eliminate a middle term, okay? And in this case, we've got a radical times itself. What do you end up with? What's inside? So we have x squared plus 100, and then minus 10 and positive 10, we have minus 100. Well, that's really nice because we end up with x squared. On the bottom, we've got x squared times this whole big thing, and I just wrote that down like that. But what happens? I got an x squared on top, I got an x squared out here, bam, I've got 1 over this. Maybe that helped. As x goes to 0, if I put 0 in here for x squared, it's under the radical and being added to 100. So I've got 0 plus 100. What's the square root of 100? 10. 10 plus 10, 20. The limit as x approaches 0 is 1 over 20. You might not have thought of that technique on your own. Now, you will think of that technique, right? When you see a radical and nothing's factoring, think about multiplying by the conjugate. Okay, that may do it. Okay. Questions on that one? We have a few like that. Sandwich theorem, and I don't honestly think I gave you any questions over this. What it's saying, the sandwich theorem, and you might not want to even write all that down, you can get it on the notes when you get there. If you've got two graphs, we've got this red guy, we've got this yellow guy, and if we know the limit of both of those and they happen where they intersect, if you sandwich this guy in between there, his limit's going to be between theirs. I mean, here, I think I wrote some other stuff here. Let's see. All right, here's a value A. And so this point where these two guys are intersecting is A, and the y value is L. So the limit as x approaches A, it's always a y value. L, limit, is a y value. Does that make sense? Okay, so we've got that, and it's equaling L. Well, this guy comes in the middle. So does it make sense that h of x, this is above, so it's the upper one, it's going to be less than or equal to f of x, and it's going to be greater than or equal to g of x. Does that make sense? Okay. And so it's sandwiched in between. And if the limit as x approaches A of g of x is L, and this one is the same thing, then the h of x is going to have the same limit, which kind of seems like common sense when you really think about it. And why did we need to have a theorem on it? But sometimes you can't find the limit of this new function, but you knew the limits of these other two, and you sandwich them in between, and you'll be able to get it. But I actually don't think I gave you a problem about that. I'm thinking that I didn't. So we'll see. I wanted you to hear the theorem. Here's an example. You don't want to do that one right now. We're moving on. We got to look at the problems that I did give you. So let's do this. I don't know why those are so small. Okay, so you have these, right? And some of these are pretty quick. All right. Find the limit as x approaches 5. So if we go here, you're looking at your graph. As x approaches 5, what's the y value there? So the limit is 0. Okay? As x approaches 5, so there's my x value. Where's my y value? My function is right there at y equals 0. So your limit's going to be a y value. All right. Find the limit as x approaches 1. Now, what are your choices? As we approach 1, what happens? We're coming in from the right, we've got this. Coming in from the left, we've got this. Do you remember about limits? If they're different coming in from opposite sides, what does that mean? Does not exist. The limit has to be the same from the right and the left. So here, we've got coming in from the right, we end up, what's the y value here? 0. So from the right, the limit is 0. From the left, the limit is 0 and 5, not the same number. So the limit does not exist. Okay, these are concepts we did cover in pre-cal, so we're just kind of easing back into it, but we did cover these. All right, find the limit as x approaches 4. As x approaches 4. What do you think it is? 4. Because here's the limit. Now, a lot of people go, but it's not defined. Remember we said the limit does not have to be defined for the function. But from the left you come in and you end up there. From the right you come in and end up there. So the limit as x approaches 4 is 4. What about this little guy down here? If I said what is f of 4, then you'd have 0. So f of 4 means where is it defined? That would be 0. But the limit as we approach 4 is up here. Okay? That makes sense? All right, so we've got those. All right, let's look at this graph. Which of the following statements are true and which are false? We have to be careful with these. All right. The limit as x approaches 0 of f of x. Okay, so as x approaches 0, does that exist? Does the limit exist? Okay, so that's true. The limit as x approaches 0 is 0. Is that true or false? False. Good. Okay, you have the picture. I'm going to make this a little smaller so I can get more on here. The limit as x approaches 0 equals -1. True. Okay. The limit as x approaches 1 is equal to 1. False. Because as we approach 1, what do we have? Two different things. Okay. Limit as we approach 1 is 0. False. The limit as x approaches, what is that saying? X sub 0 exists at every point in the interval -1 to 1. So between -1 and 1, is the limit exist everywhere? Yeah, yeah. Because everywhere on here, now the function's not defined everywhere, but the limit exists everywhere in that interval. Okay. Is that okay? Confusing, but okay. All right, so we're moving on down here. Okay, find the following limit. Can you direct substitute? This guy's polynomial. There's nothing on the bottom. We don't have to worry about anything. Can we do direct substitution? Yes. So just take -1, plug it in here. Your answer's already there for you. So just verify that. So you get -10. Everybody got -10? Okay. All right. So you're going to get several at the beginning of your homework where direct substitution is fine. Just do it and you'll be fine. Can we substitute here? The limit as x approaches 1. Not a problem. So we have 1 plus 2 over 1 plus 5. And so it does exist, and you'll put 1/2 in the box there. Okay? Okay? Is there any reason we cannot substitute -9 into here? We could substitute. Okay, let's try it. 18 minus -9, all of that raised to the 4/3 power. Okay? You could do it in your calculator. You could actually do it in your head, because what's 18 plus 9? 27 to the 4/3 means third root or cube root of 27, which is what? 3. 3 to the 4th is 81. So you could do that in your head. I'm not saying you'd want to, or in theory you could do it in your head. Okay? If you have a fractional exponent, remember the bottom of the fraction is the root, the top of the fraction then is raised to that power. Okay. So let's get to one right here. Is there a problem with this guy? The limit as h approaches 0. No, because we've got 2h plus 1 under the radical. So we can plug in okay. So what's the square root of 1? So we got 2 over 1 plus 1. Just 1. Okay. All right. Okay, I think number 7, we have a problem. That sounded like Houston. We have a problem. Okay. All right, the limit as x approaches -2. If I plug in -2, I get -8 plus 8. That goes to 0. So I cannot do that. Doesn't work, so what are we going to try? Factoring. Okay. What can we factor out on the top? Okay, negative 2 times x plus 2. What's on the bottom? What can we take out? And you're always happy when you see the same thing on the bottom. That's good. And so bam, bam. So we have negative 2 over x squared, the limit as x approaches negative 2. And what's that going to equal? Okay, negative 1/2, because it's negative 2 over 4. Are we good? Okay, now the next one is that thing with the conjugate, and I'd really like you to try it on your own and see. You've got an answer there to try to get to, so let's try to get to that one. What could we multiply by? Yeah, we should be able to do that. Actually, that's not going to help you. Okay, on this one, and you're not going to see this a lot of times, this is x minus 225. When I see 225, do you think square root? I mean a perfect square? Okay, that's the square, perfect square with 15 as the root, right? So and you're looking up here, could we rewrite this? You might not have thought of it, but if we did square root of x minus 15 times the square root of x plus 15, does that give us that thing right there? Square root of x times square root of x is x. We don't have a middle term, and we have minus 225. Well, now what's on the top? Bam. So we have 1 over, whoops, Leland, don't leave me, square root of x plus 15. Can we plug in 225 there? Yeah. So 1 over square root of 225 plus 15. So 1 over 30. The reason you might think to do that is because you're looking at 225, you're seeing perfect square, you're looking up here. You might not have done that before, but you will do it now. It will be a technique that's in your head. And we don't usually think to factor x into square root of x and square root of x, but in this case, since it was up here, it kind of comes to mind, or maybe it will. Okay, I think maybe the next one is the one I was thinking of. Yeah, here we go. All right, this is the one you want to do. And so what will our conjugate be? Square root of this thing plus 5 over itself. So let's write that, and you guys try it. You're looking for an answer of 2/5. So there's all the work for that, and just, you know, it's a good technique, and when you see a radical, you want to at least think of that. All right. Okay, that's a trig one. Okay, can we just direct substitute? Can we take the sign of 0? What is it? 0? Okay, so if I plug in 0, I get 6 times 0 minus 1, so what's my limit? -1. Okay. And these look ugly. You just see these, and you just go, ooh, no, I don't want to do those. But they're really not bad, unless you end up with 0 down here. But what is the cosine of 0? 1. So if we just plug in, we get 5 plus 2 times 0 plus the sine of 0 over 6 times the cosine of 0. Okay? So what do we end up with on the top? Just 5, because that's 0 and the sine of 0 is 0. And on the bottom we have 6 times 1, so we have 6. So it's really not that bad. You just have to remember your trig stuff. Okay? All right. Let's try 12. Okay. Can we plug in for this guy? The limit as x approaches negative 4 pi. It's really not bad. You're just plugging in. What do you get? Get that times the cosine of negative 4 pi plus 4 pi, which is what? Cosine of 0, which is 1. And so 1 times this is just that. And they rewrote it this way. I don't think Math Lab would count it wrong if you put it in this way, but they transferred the numbers. Okay, I think the last couple of things are just doing the limit as x approaches 0, and you're using this thing, which we've done a good bit. So I think we're probably good. Do you think we're good?